So today we'll do cosmology and no formalism at all. Almost. So it's going to be a little bit towards the end. But it won't be formal math. It will be just mathy. So it'll be cosmology. And I invite you to make it a bit more interactive, if you like. Just ask questions throughout. OK. Oh. There you go. So we were looking at the evolution of Friedmann-Lemaitre spacetimes. Roberts and Walker were also involved, but a little later. Let me remind you, depending on what is the major contribution to the energy momentum tensor, we will get a corresponding equation of state. Equation of state meaning the relation between pressure and energy density. The universe has always been filled with various different things: radiation, matter, dark matter, dark energy, and so on. There's a mix. And at every given time, maybe one of them is dominant. There will be transition periods too, but usually one of those contributions is dominant. And then during that time when one of those contributions is dominant, there's going to be a relatively constant relationship between the pressure and the energy density. Periods of time in which this relationship is constant and linear, which is not always the case, but there are long periods or clearly defined periods in the evolution of the universe where there is a constant linear relationship between pressure and energy density. So the pressure as a function of the energy density is some constant W times the energy density. Such periods in the evolution of the universe we call an epoch. An epoch is a period in which that relationship is a constant one, where the pressure is some constant multiple of the energy density. Most important are these epochs, these types of epochs. Epochs can occur several times. For example, we assume that there was a very early period of domination by energy density, by a effectively cosmological constant, and also a late period. So particularly important types of epochs are these. Radiation-dominated epochs, where the W parameter is 1/3. That's simply the number that you get when you take the energy momentum tensor of electromagnetism and check what the relationship is between the energy density in a photon gas and the pressure of that photon gas. It comes out to be 1/3. Another important type of epoch is that of matter domination, the epoch where the energy momentum tensor is dominated by the matter contained in galaxies, and that includes dark matter. In this case, the assumption is that this matter is effectively pressureless. A gas of galaxies is not having a significant pressure, where the galaxies would bump into each other. So when there is no pressure, then the relationship between pressure and energy density is characterized by the W parameter being equal to 0. Okay? So the matter-dominated epoch is characterized by W equal to 0. And then a very important type of epoch is the energy-dominated type, the dark energy dominated type, where the pressure is the negative of the energy density. W is equal to -1. In each epoch, so whenever W is constant, we can use that relationship between the pressure and the energy density in the continuity equation that we had at the end of the last lecture in order to derive a relationship, the functional dependence of the energy density on the scale factor. So what's going on here is this. We have the continuity equation, which we can derive rigorously from general relativity. And the continuity equation basically says that, it's a relationship between pressure, volume, and energy density. And if you know how the pressure and the energy are related to each other, and during an epoch, they are very closely, very easily related to each other just by proportionality, then you can plug that into the continuity equation, and it becomes this equation here, and you can solve it, and then you find out the solution of that differential equation is rho of A, which is telling you how energy dilutes, how the energy density behaves as the scale factor changes. So once you know the relationship between pressure and energy density, you can use the continuity equation to find out how energy is diluting. This is the differential equation we have to solve. So energy density as a function of not time, but the scale factor, right? So we have a differential equation of rho of A. If W is equal to a constant, then we can solve that equation here. And you can solve that differential equation. This is the solution. Please check. The solution is that the energy density is diluting with increasing scale factor as the universe is expanding. Or in fact, you could also use it for a shrinking universe in this way. So the energy density is diluting in a non-trivial way that depends on the W. If we were dealing just with a gas of galaxies, a pressureless gas of galaxies, then we would expect that the energy density in the universe is simply the accumulated mc squared of all the matter in the galaxies, in which case we would expect that the energy density dilutes like a to the power of -3. Simply the volume increases, the matter stays the same. So it has to dilute with 1 over the volume. And that is indeed the case if you choose W equal to 0. W equal to 0 is the pressureless gas case. And then we have a to the power of -3. But let us look at all the epochs that we considered earlier. So in the matter-dominated epoch, where W is equal to 0, we have that the energy density is some constant rho matter times a to the power -3. If the W parameter is 1/3, that's characteristic for an epoch of radiation domination, then we see that the energy density actually scales with the scale factor to the -4th power, which means that the energy density in the universe drops quicker than you might expect from mere dilution. And the reason for that is that the photons not only get diluted in an expanding universe, but on top of that, their wavelength also gets stretched, because the space underneath them is expanding, and so the wavelength gets stretched. And that's an additional linear effect, because as the wavelength of a photon gets stretched proportionally to the scale factor, its frequency drops, just with the inverse power. But the frequency is proportional to the energy of the photon, h bar omega, right? Or h bar over lambda is the energy of a photon, and as lambda is increasing by a, we see that additional drop by 1 more power. On the other hand, there is the epoch of dark energy domination, where W is equal to, do you have a question? Yeah. Just a moment, please. Where W is equal to -1. And in this case, we see that in the exponent, we actually have a 0, a to the power 0, and the energy density is constant. This is quite dramatic, it means that dark energy does not dilute. As the universe is expanding, dark energy density stays constant. You get energy for free, so to speak. It's just multiplying. Yes?
So the way these things dilute make intuitive sense, but should it be surprising that they make intuitive sense given the fact that there's no time-like killing vector fields in this space-time? Energy shouldn't
yeah, it's a little bit surprising. Even the continuity equation. Remember that we derived it ad hoc using classical arguments, but on the other hand, we can also derive it exactly like that from general relativity. I'm not sure what the deeper reason is for why often in general relativity you can get to the right answer just on the basis of classical reasoning. I suppose it has to do with, one intuition is units, simply. You see, the units have to work out. For example, for the continuity equation, the units have to work out. If you wanted to modify the continuity equation, then it's not easy to do that while keeping still the units consistent. And I think that's just a general feeling for why sometimes you can even guess the right equation just on the basis of unit considerations. Sometimes you may be off with that because there could be unitless quantities that occur all over the place, but it's not easy to get unitless quantities doing non-trivial dynamics. Whenever you have tensorial equations, of course, then you should expect that generically the GR case will differ from the classical case. But in this case, the quantities are basically scalar, so it's difficult to get non-trivial tensorial behavior in it. By the way, let's look just for fun at the case where if W is smaller than -1, and some experimental indications are there that it might be smaller than -1. We can't really account for it with any reasonable fundamental theory. The usual quantum field theories don't give us a W smaller than -1 under any circumstances, or at least under any plausible circumstances. But GR doesn't care. General relativity says, well, okay, whatever your matter does. And if the matter comes with a relationship between pressure and energy density that has a W smaller than -1, we can absolutely put that into the equations, into the Friedmann equation and the continuity equation. They still hold true. So what does that mean then? Well, then the energy density is a constant times a to the power of some epsilon, which is larger than 0, right? If W is smaller than -1, this thing goes negative, which means that the whole exponent goes positive, which means that with an expanding universe, the energy density is not diluting, it's actually getting larger, right? So it means that the energy density is anti-diluting. In the case of pure dark energy, W equal to -1, the energy density is constant. If W drops below -1, the energy density is actually increasing over time. And we will later see what that means for the evolution of the scale factor, what that means for the time dependence. It means something rather dramatic. Okay, so now that we have rho of A, at least for those epochs here, for these epochs we have rho of A, we can apply that in the Friedmann equation. Remember, the Friedmann equation took this form here. You have A dot over A. The K indicates the curvature of the overall curvature of the spatial part of space-time. K is positive means positive curvature. K0 means no curvature. K negative means negative curvature. And here we have the energy density. You see, we have now rho of A. From here, we can plug, for each epoch separately, we can plug that rho of A into the Friedmann equation. And then this equation simply becomes a differential equation for A as a function of t. So we can obtain then the evolution of the scale factor and therefore the expansion of the universe. In principle, if you remember, the Friedmann equation had here also the cosmological constant. But we are dropping it now because we are, by convention, including the cosmological constant, if it is there, in the energy density. So if there is one, it's part of the energy density. We don't carry it around separately. All right, so the observational evidence is that the universe is on large scales. The larger the scale is that you look at, the less curvature there is in space. If you look at a triangle that's whose sides are a few billion light years across, the sum of the angles is very accurately 180 degrees. And there are many other pieces of corroborating evidence that tell us that the universe is on large scales pretty much flat spatially. So k equals 0 is a good model. This equation simplifies, the Friedmann equation simplifies even further when we choose k equals 0. Then it just tells us that a dot over a squared is proportional to rho of a, where the rho of a is, of course, given by those three possibilities if we choose one of those epochs. If we plug that in there, and again, that's something for you to work out as an exercise, and you can also put it in the project. Plug it in there and solve the differential equation. Actually, in the project, it might be nice to also choose k not equal to 0 to see what difference it makes for the overall evolution, whether or not the universe is closed or open or flat. So if k is positive, 0, or negative. Yes, so if we plug those rho of a from the three types of epochs into that equation and solve it then, actually we don't even have to choose a particular epoch. We don't even choose a particular epoch just yet. If you just say that it's one of the epochs and we keep the w arbitrary but constant, then we can solve that differential equation here, and that's the solution. So in an epoch of constant w parameter, this is the evolution of the universe. The scale factor behaves like this with a certain power. So the scale factor is a dimensionless quantity. It literally scales everything up. And so here we have the actual time, the cosmic time, as measured on the wristwatch of somebody who's traveling along with the galaxy. It's co-moving with the universe. In other words, somebody who doesn't have any peculiar velocity, somebody who is not traveling very fast, it's only going with the flow of the galaxies. And that is some unit of time t naught, so that the whole thing becomes unitless, and then you have this power here. So the universe expands with a certain power of t. And we can check now for the various epochs, for the various w's, what kind of scaling, what kind of expansion that is for the universe. Well, expansion or shrinkage. You see, because a dot over a arises in the Friedmann equation squared, for every solution with a dot positive, there is a solution with a dot negative as well. So you also have shrinking solutions that have the same scaling behavior. So for the case k equals 0, under the assumption that there is no spatial curvature, the universe is R3 as far as the spatial slices are concerned, we have this behavior then. Maybe I should show both equations. Yeah, okay, so let's specialize now to the different w's of the different kinds of epochs. Let's say we consider the epoch where W is equal to 1/3. That's the radiation-dominated kind of epoch. Now, when W is equal to 1/3, then we have here 4/3, which means 3 times 4/3. It's just 4 here. There's a 2 over 4, that's 1/2. So we have that the universe is expanding with t to the power of 1/2. So while the energy momentum tensor of the universe is dominated by radiation, and that was the case in an early period of the universe, as we will see a little later, the universe was expanding as part of a parabola this way. You know, a parabola 90 degrees tilted. So this is a parabola. So it's expanding, but the expansion is slowing down like that. On the other hand, let's look at a matter-dominated period. Remember that radiation dilutes faster than matter because radiation also has its wavelength stretched. So after a radiation-dominated epoch, there should be a matter-dominated epoch. And in a matter-dominated epoch, the pressure is 0. The W parameter is therefore 0. If the W parameter is 0, then the power here is 2/3. So now we have this kind of behavior. So the universe is still expanding, but now it's expanding with a slightly larger power there. Instead of 1/2, it's 2/3. But it's still decelerating. It would be a constant expansion if it were just a straight line here, right? But no, it's decelerating here and there. It's just not as fast decelerating as in this case. And that's because matter is diluting less fast than does radiation. By the way, you may want to calculate under which circumstances it would be constant. Now, a very important case for model building in today's cosmology is the case where this is a large power, where this is not t to the power 1/2, t to the power 2/3, as in radiation or matter domination. No, it is assumed nowadays that in the very early period, at the very early epoch of the universe, as I will discuss a little later, this was actually a very large number. So that the universe was almost exponentially fast expanding. It was expanding with approximately a very large positive power. That is called an epoch of power law inflation, power law expansion. That's an epoch when this is a large number. Let's call that number R. We can calculate what W then has to be. For R to be a really large number, what does W have to be? Well, let's see. If we want a universe that where the scale factor goes like t to the power of R, where R is a very large number, then W has to be, well, W is -1 plus 2 over 3R. That's simply saying that this is equal to R, right? If this is equal to R and R is large, then we must have that this expression, the W is this expression with R very large. What you see from this is that if R is very large, this denominator is very large, this number is very small, and therefore the W parameter is just above -1. Okay, so keep that in mind. A period of expansion in the universe where the scale factor goes like t to a large positive power is a period in which the W parameter is just above -1. Because that's just a small positive perturbation away from -1 here. What would be happening in the extreme case where R goes to infinity? In other words, where this goes to 0, where the W parameter goes to -1. In this case, it would seem like we get an infinitely large power. The scale factor, A of t, scales like t to infinity. That doesn't make sense. In fact, we have to, in this case, we have to solve the equation afresh. And we find that, yes, there is a solution for W equal to -1, and it is the exponential function. So if W is equal to -1, in other words, if the energy momentum tensor is completely dominated by a cosmological constant, then the scale factor increases exponentially. But as soon as W is not exactly -1, but a little bit above -1, we have a power law inflation where the universe expands with some large power. Now you see that these two cases, the power law expansion and the exponential expansion, are qualitatively quite different from those cases of matter and radiation domination. And what is most strikingly different is that these are cases of accelerated expansion and these are cases of decelerated expansion. An epoch in which we have accelerated expansion, that is to say an epoch in which a double dot is larger than 0, is what is called an inflationary period. And we may check what it takes to have an inflationary period. What value does W have to take such that this equation, this behavior turns around and we go from deceleration to acceleration? What's the threshold? Remember, I asked you a little earlier to think about what the threshold is. When would it be linear? When would it be constant? Well, let's look at this. The threshold is at W equal to -1/3. Let's calculate that. If you take 1 minus 1/3, then you have 2/3 divided by 2/3. So you have a power of 1. Okay, so that's the threshold. If W is equal to -1/3, then the scale factor is just coasting, right? The universe is just not decelerating, not accelerating its expansion. Which is a curious value if you think about it, because it means that it's not sufficient to have negative pressure. If W is like -0.1, then the pressure is a negative value for every positive value of the energy density. But that alone is not sufficient to make the universe accelerate. No, the negative pressure has to be sufficiently strong. The relationship has to be at least 1/3. The pressure has to be at least -1/3 of the energy density in order to achieve that the universe is expanding. That's the threshold value. Sorry, that it is expanding in an accelerated fashion. Okay. Again, solve the equations yourself to check that you really get exponential inflation, because we only did it for the power law case and the other above case. We didn't actually solve it for the exponential case. All right, so now we know what inflationary epochs are. W smaller -1/3, which is to say that the universe is expanding in an accelerated fashion. So here's an overview of, how did that happen? Oh, here we go. Here's an overview of how the universe most likely went through various epochs. So that's a slide that's a bit busy. And if you have any questions, do ask me about it. let's start with the present time. Today, plus minus a few billion years, actually like today, a few billion years earlier, we have a period of accelerated expansion. A Nobel Prize was given for the discovery that the expansion is actually accelerating. We are not in any one of those regimes, matter or radiation domination, radiation or matter domination. We are in this kind of regime, or perhaps that kind of regime. Not dramatically, the acceleration is subtle. So these are not large powers there. But the W parameter seems to be smaller than -1/3. In fact, the evidence points towards it being perhaps even smaller than -1. Okay, so we have a period of accelerated inflation, accelerated expansion. Sometimes I'm using the term expansion and inflation synonymously, but that's not entirely correct. It's an expansion only in inflation if it's accelerated. But in this case, it is accelerated. Okay, so that period started a few billion years ago. And on the clock that measures cosmic time, we are at about 10 to the 19 seconds now. That's how late it is at the moment. If somebody asked you for the time, you know, this is roughly the answer. This is meant to be a logarithmic scale, because otherwise this would go from here to very, very far. So what was before? In the first few billion years of the universe, like from, I don't know, like the first million years to the first 3, 4, 5 billion years, the universe was matter-dominated. So from about 10 to the 13 seconds up until about 10 to the 19 seconds, matter was dominating. So the universe was still dense enough so that the energy momentum tensor was dominated by the galaxies and their dark matter. Dark matter making up actually more of the matter than the visible matter. Yeah, actually, here are the numbers. The best fit today is that k is equal to 0, no spatial curvature on large scales. I mean, on small scales there is, of course. That's why the moon goes around the Earth. But on large scales, there's no overall curvature. So k equals 0 is a good approximation for a cosmological model. The best fit says that the contributions to the energy momentum tensor are having these proportions. About 70% of the energy density is due to dark energy, something that produces a negative equation of state parameter, and that doesn't seem to have its own spatial dynamics. It seems to be completely homogeneously distributed over the universe, in distinction to dark matter, which definitely is clumping. Then, so that's 70% of the energy density in the universe. About 30% of the energy density is in matter, and of that matter, about 90% is dark matter, and only about 10% is visible matter. Okay, so today is about 10 to the 19 seconds. At about 10 to the 13 seconds after effectively the Big Bang, I'll speak a little bit more about the Big Bang in a moment. At about 10 to the 13 seconds, that's when matter took over from radiation. Before that, the universe was radiation dominated, or the energy momentum tensor was radiation dominated, and after that it was matter dominated. And part of that, in that matter domination epoch, was the phase transition that led to the cosmic microwave background. That was about when the universe was about 100,000 years old. that's when the nuclei, the protons and the electrons were cool enough so that they could stick together and then formed hydrogen. And hydrogen gas, as opposed to a hydrogen plasma that was there earlier, hydrogen gas is transparent, and the photons that were not able to travel very far in the previous plasma of hot ions, of protons and electrons, because photons bump into charges all the time, photons were free to travel as soon as protons and electrons had found each other and formed hydrogen gas, because hydrogen gas is transparent. So the cosmic microwave background that we see now consists of light that was around and bouncing between protons and electrons while the universe was still so hot that it was a plasma. Light that then continued to travel when the universe suddenly became transparent, as suddenly the energy dropped, the temperature dropped sufficiently so that hydrogen gas could form. Anyway, somebody said that hydrogen gas is a wonderful gas. You could make a dictionary entry or an encyclopedic entry where you could say hydrogen is a transparent gas that, given enough time, turns into people. Right? Because that's what it does. I mean, there was only hydrogen at the beginning. Okay, but then what before? Before we had an epoch of radiation domination. And we know what the W parameter in that case is. And we had phase transitions happening in there, several phase transitions. For example, at some point early enough, it was hot enough so that nuclei were no longer stable or were not yet stable. And so they were, strong phase transitions and weak phase transitions. We don't know exactly all about those phase transitions, but we know actually quite a lot. I mean, it would seem that as soon as we go back to less than a second, nuclei formed when the universe was on the order of seconds old. You might think that, okay, now it's getting really speculative, right? I mean, you're talking about what the universe did when it was a second old. How can we possibly know that? The thing is, we know that pretty well. And the predictions match experiment very nicely. And the reason is that we can actually test that. We can actually, in the lab, create the temperatures that were prevalent when the universe was this dense. It's not hard. The universe wasn't actually very hot at that time compared to the energies that we can create in the lab. You may wonder, okay, so how far can we go back in experiments in the lab? You see, this is a timeline. This is early time. It also means higher temperature. The earlier you go back, the higher the temperature, which also means the higher is the energy of typical collisions between the particles in the universe. And you can ask, well, how far can we go back in time? How far can we go back in temperature? How far can we go back in collision energy until we meet the collision energies that we can now probe at CERN? And the answer is 10 to the 11th seconds. At CERN, you can test physics down to those energy scales that were the typical energy scale of collisions of particles in the universe when the universe was only 10 to the power minus 11 seconds old. So this far we know the physics. And that's neat, because you do the physics at CERN, you get actually, even nuclear physics, it gets you already here. You do the physics there, and then you calculate how those phase transitions are supposed to have happened, and therefore what proportion, for example, of hydrogen and helium you would expect to be coming out of that process here, of the cooling process of the universe. And that matches pretty well the observations, which is nice. You do experiments in the lab, you check out the sky, and you get from completely different sources consistent results. Yep.
Right, so where would the phase with plasma was formed? Where would that be exactly on that line? Where like the plasma, the quarks, and you said the electrons, where the photons couldn't travel, so hydrogen was not formed. Where would that be exactly in the timeline, like that phase where hydrogen gas was not formed?
Okay, so the hydrogen gas, okay, so this was at about 3,000 Kelvin. 3,000 Kelvin were reached when the universe was about 100,000 years old. I don't know exactly what that is in seconds. Okay, but then if you go further back, you get other phase transitions, not just the proton-electron gas becoming proton-electron plasma becoming hydrogen gas, but there's also there's also the strong phase transitions and weak phase transitions. I mean, you can have that. Oh, sick. Yeah, and in the lab now they are probing quark-gluon plasmas, for example, and that is probing what presumably happened in the universe too. It was so dense, so hot, that the quarks and gluons were not yet ready, not yet cool enough to form mesons and baryons. And of course, at sufficiently high energies, particles don't have mass because the electrovaric phase transition hasn't happened yet, and so on. Now, it's assumed that the radiation-dominated period goes back all the way to the time of 10 to the minus 32 seconds. You can't really probe that in the lab so far back. This gap between 10 to the minus 11 seconds after the Big Bang, in quotation marks, and 10 to the minus 32 seconds after the Big Bang, this gap is corresponding exactly to the gap between the energies that the LHC can reach and the Planck scale. Or what is not quite the Planck scale, it's almost the Planck scale. This is that same gap, which is great because it means that if we can probe that astronomically or astrophysically, we are effectively probing what LHC cannot. Well, and it is assumed, it fits the data best, it's the standard model of cosmology, to assume that before 10 to the minus 32 seconds, for reasons that we will discuss now, there was an epoch starting from about 10 to the minus 43 seconds to 10 to the minus 32 seconds, where we had that the universe was dominated by dark energy, where the universe was dominated by, where the energy momentum tensor was dominated by something that drove its W parameter towards -1. And that is called the period of cosmic inflation. W is assumed there to have been about -1 plus some epsilon as a good approximation. So power law inflation is a reasonably accurate model. It's not the best model available, but for our purpose, it's very close, and we don't need to worry about the other subtleties. We are not so sure about them anyway, experimentally or theoretically. And before 10 to the minus 43 seconds, well, we have no idea, because that would be the Planck time. Fluctuations of curvature would be so dominant. I mean, the interplay of general relativity with quantum theory would be so strong that with the tools of classical general relativity, we have no expectation of being able to cover that period there. Yeah?
So what turns off inflation? Because as far as we saw, it doesn't dilute, right? So
that's right.
Why does it happen that we had these few?
Very good question. Very good question. If we have a cosmological constant here in that period, then yes, it explains why the universe would explode, why it would expand exponentially or almost exponentially with the power of a very high power, but why would it ever end? Because the energy density is not diluting. Well, the answer is that we don't believe that it was a cosmological constant. We believe that it was the potential of a scalar field that produced effectively something like a temporary cosmological constant. Remember that the potential of a scalar field contributes to the energy momentum tensor in just the same way that the cosmological constant would. It drives W towards -1. And when that potential drops, then the cosmological constant effect goes away. It no longer presses W towards -1. And that's how it is assumed that that inflation ended. In fact, that ending of inflation is characterized by that energy that was in the potential, since the potential dropped, that energy going elsewhere. Do you have any idea where it might have gone? So during that period, the potential of the inflaton field, of a scalar field, was elevated, very high, almost Planck scale. Very high energy, and not diluting at all. And then at the end of the inflationary period, the inflaton potential has made its way all the way down. The field phi has, the inflaton field has reached the values that its potential is now low again. But where did that energy go? It went into the production of us. It went into the production of matter and radiation. That energy produced the initial particles in the universe and made it very, very hot, because there was a huge amount of energy. Made it very, very hot, and therefore at the end of inflation is the starting point of what you might call a Big Bang. From the end of inflation onwards, everything is just as ordinary Big Bang cosmology would have it. At this point, you have a very hot universe that expands, but expands in a decelerated way, in the conventional way. So everything from here onwards is ordinary Big Bang cosmology, preceded by an inflationary period. And what started inflation, we don't know. It's too speculative, but there are great ideas about it. And I'll tell you in a moment some of the ideas there. Okay, but what made people think that there is an inflationary period? Why not just say that there was a Big Bang at this point? Right? I mean, we could just imagine that the radiation-dominated period goes further back to time equals 0. And that's where we had a Big Bang. And the universe just bang came into existence. Why not that? Why instead, assuming that there was an inflationary period preceding this? You know, it seems hardly distinguishable. It's 10 to the minus 32 seconds. Why bother even with this little amount of time? I mean, you blink and you miss it, right? It's like 10 to the minus 32 seconds. No, but there are really very good reasons to believe that there was an inflationary period before the hot Big Bang. Okay, so this arrow points towards the reasons for why inflation, right? So one of the problems that is addressed by the assumption, the model of having an inflationary period, is this. It's the flatness problem. It's one of several problems. You see, inflation is appealing because it answers several fundamental questions at once. It's therefore conceptually quite appealing. So here's the flatness problem. Let us reconsider the experimental finding that the universe is basically flat. As far as space is concerned, it's just R3, k is equal to 0. Let's see what the evolution is of a deviation from flatness. What if the universe is not exactly flat? It has some positive curvature. How does that curvature evolve over time? Or if the universe has some negative curvature, how does that curvature evolve over time? The answer is dramatic. The answer is that it's highly unstable. If you start out your universe with just a tiny bit of positive curvature, this will quickly get out of hand, and it will have a lot of positive curvature. If you start it out with negative curvature, then by now it would have a dramatic amount of negative curvature. But we do see that the curvature is basically 0, which means that early on, the curvature must have been 0 with enormous accuracy. So the question is, what tuned it? What tuned it to be so flat? So let's derive first of all, that problem. We take the Friedmann equation, here it is, unchanged, and we absorb the cosmological constant in the energy density so that we don't have to carry it around separately. So the Friedmann equation now looks like this, where I've also introduced a new variable just for convenience and because it comes up in the literature all the time. The ratio of A dot over A is also called the Hubble parameter. When Hubble first noticed that A dot over A is an important quantity to study, he didn't know that it changed over time. It was initially called the Hubble constant. But now we know, of course, that this ratio can change over time, so it's a Hubble parameter. So H, the Hubble parameter, is a function of time, just like A dot over A is a function of time. Only, I mean, if we had a period of exponential expansion, then that would be a constant. Okay, so if we express A dot over A as H, and we have an H square here, and we absorb the cosmological constant in the energy density, then this is the Friedmann equation. From this, we can draw a very, very important conclusion. Namely, if the universe is to have, at any given time, if the universe is to have zero curvature, zero net curvature in space, remember, I'm always being picky about this because in time, it has curvature, the universe, right? There's curvature between space and time. That's what expansion means. But decay labels the spatial curvature alone. So if the universe is to have zero spatial curvature, if this term is to be absent at any moment in time that you might be interested in, if the universe is supposed to have no curvature at a particular point in time, then the Hubble parameter squared has to be equal the energy density, total energy density, taking everything into account, dark matter, dark energy, everything into account, right? It has to equal that. Or, and that is the way we want to look at it now, if the curvature is to vanish at a given point in time, the energy density has to have a particular value given by the Hubble parameter squared. So what this tells us is, for example, if we take the present day, we take measurements of A dot over A, so we basically measure what the Hubble parameter is now. So at what rate it is not accelerating, at what rate the universe is expanding now. And that's one set of measurements. And then a completely different set of measurements gives us what the energy density is in the universe. If they are equal, then the curvature is vanishing. In other words, whenever you know what A dot over A is, at any point in time, you can calculate what the energy density has to be for space to be flat. There is a critical energy density. If that energy density is a little higher, then the universe has to be higher than the critical energy density, then the universe has to be positively curved. If the energy density is a little lower than the critical energy density, then it has to be negatively curved. The critical energy density is not just some universal number. The critical energy density, the threshold energy density, is determined by A dot over A. So at every point you have to reevaluate again. You know, for this A dot over A, you get a certain critical energy density. If you are exceeding that, you have positive curvature. If you are lower than that, then you have negative curvature. So the critical energy density that the universe must have in order to be flat in space is this. Critical energy density is up to some prefactors that. And at the moment, that's where we are at. If you measure this and you measure that, they seem to be agreeing, not with many digits behind the comma, but they are basically the same. Same order of magnitude at the very least. I'm not saying that we measure deviations of this. I'm just saying that the error bars are still relatively significant. Okay, so we see that today, measuring A dot over A, measuring the energy density, means that this equation is approximately fulfilled. The universe is flat. And we can also check it geometrically with the CMB and all that. But assuming that that's the case, or given that that's the case, we should be able to calculate how close to critical the energy density was earlier. Because we can run the evolution of the universe backwards. We can calculate in particular how close it was to critical, how close the universe was to being flat earlier. For this, let's introduce the omega parameter. The omega parameter is the ratio between the actual energy density of the universe and the energy density that it needs to have to be flat. So this is, omega of t is measuring the closeness to flatness. If omega of t is equal to 1, the universe is flat. If it is larger than 1, it's positively curved. If it's smaller than 1, it's negatively curved. So the total energy density, the actual energy density, can be written as this omega parameter times the critical energy density, but the critical energy density is given by 3 over 8 pi g h squared. So we can now replace, in the Friedmann equation, we can replace rho total by this dimensionless parameter times the h squared. So the Friedmann equation now becomes this equation. It's still expressing exactly the same as what it did before. We didn't put any new information in there. We just use new variables. Instead of looking at the rho total, we now have the omega. Okay, so the Friedmann equation becomes this equation. You know, the rho total used to be here, but the rho total can be written in this way. So the Friedmann equation is now this equation. Remember, omega equal to 1 means flatness of the universe. And here we have omega minus 1. So if the universe is flat, this has to be 0. And you see, consistency. If the universe is flat, k is equal to 0. Fine. Right? So that's consistent. If k is equal to 0, the right-hand side is vanishing. If the universe is flat, then the left-hand side is vanishing too. Everything seems fine and consistent. But there's way more that we can read off from that equation. Namely, assume that the universe is a little bit positively curved. K is positive. Then what happens over time? Well, as the universe is expanding, and as the universe is slowing down, right, it is expanding, the A dot is diminishing. Right? So the universe is expanding, but it's slowing down its expansion. So the A dot is dropping. Well, if A dot is dropping, then the denominator becomes smaller and smaller. This number becomes larger and larger. The deviation from 0 of this thing becomes larger and larger, which means that the universe becomes more and more curved. If we started out with a small difference, if omega started out almost 1, over time, that difference can become much, much larger. Well, let's calculate that in some examples. So for example, let's take the matter-dominated epoch. Remember that then the scale factor goes like t to the power of 2/3. It's, you know, like this type of parabola there, a to the power of t of 2/3, which means that a dot goes like t to the power of minus 1/3. So that means that this goes to 0, like t to the power minus 1/3, and so we have that divergence. Let's formulate it in this way. Let's look at the ratio of closeness to flatness at time 1, at time t1, and this is the closeness to flatness at time t0 earlier. Then this scales like that, just because of this. This is now a nice way of expressing things because the parameter k dropped out. K is dimension full. And these are dimensionless quantities. So let's assume that this is a small number that we started out with. Let's assume that this is a small number. That's the closeness to flatness that we have now. This is the closeness to flatness that we had at an earlier time, t0. So let's say t1 could be now, t0 could be sometime in the past. So we know that omega of t1 minus 1 is close to 0 now, order 1, let's say, to be generous about it. Then much earlier, let's say at a time 10 to the minus 6 times t1, that would be when the universe was about 10 million years old. When the universe was about 10 million years old, then that ratio here, you see, if that ratio here is 10 to the minus 6, then we have that 2/3 of this gives us 10 to the minus 4. 2/3 of the power, right? 2/3 of the power. So we see that the universe was much closer to flatness then. If it is today close to flatness with an accuracy of 1 order of magnitude, then it was close to 1 part in 10,000. That's when the universe was a millionth of its current age, which is about 10,000 years old. But what if we run things further back in time? Let's say we assume that there was really a big bang, and at time t equals 0, we had a big bang, and we can go back to arbitrarily far, like 10 to the minus 30 times today's time. What then? That's not a completely unreasonable time, because if we go back by 30 orders of magnitude in time, that brings us back to the time 10 to the minus 11 seconds, when the universe was about 10 to the minus 11 seconds old. And this is, if you remember, the time when the collisions in the universe, the particle collisions, had about the same energy as what we can do with the LHC now. So this is still safe physics. We think we know everything that happens when particles smash into each other with that kind of energy. So if we go back 10 to the by 10 to the minus 30, by a factor of 10 to the minus 30 in time, then we shouldn't really use just the matter-dominated behavior of the scale factor, but also the radiation-dominated behavior. And that makes it even more dramatic, because there is a more dilution, and instead of the power of 2/3, you have a power of 1/2. One moment, please. If you do that, you find that the closeness to flatness, that early on would have to be to about 24 digits behind the comma. So just because the universe today is almost flat, with an accuracy of about 1 order of magnitude, so it could be deviating by like 10%, 90% even or so, even though we know it better than that, then at that time that is still accessible to LHC physics, we would have that the universe had to be flat with an accuracy of 1 part in 10 to the power 24. Otherwise, the universe would be much more noticeably non-flat now. That's the flatness problem of cosmology. Guillaume.
This whole discussion, we assumed that the curvature was null to find the solutions for the different epochs and whatever, and now we're plugging in, this assumes, well, I guess, for close to flat, then our solutions are probably accurate. But what would happen, if order 1 off of flat, we're starting to have a significant spatial curvature. I know we haven't seen the solution to the full equation with spatial curvature, but what would that mean? Would that mean that we would have, complete deceleration of the expansion and a big crunch or something like that? Or are we going to see
Right.
that?
So okay. So we do it in one way. We say that now it's almost flat, and if we go back in time, then we see that it was dramatically flat because of that, because the Einstein equations are unstable. The universe must have been extremely close to flat to be still as flat as it is now. Of course, if you hypothetically considered a universe that was at this early time significantly non-flat, then now it would be very curved, and we would have to, in principle, worry about the approximation that we made that the universe is homogeneous and isotropic. In fact, this calculation is not really stable because the universe has, because general relativity is highly nonlinear, and not only do we have this extreme sensitivity of curvature not being stable. You see, zero curvature is stable. If you have zero curvature at one time, you have zero curvature at all times. We saw that in the equations. Positive curvature is not stable. It will become much more positive. Negative curvature will become much more negative. But it's not just that. It's also that homogeneity and isotropy are not stable. So if you have a little bit of inhomogeneity, it will be a much larger inhomogeneity much later. If a little bit of non-isotropy, that too would happen. And so, as you said, things would get completely out of hand. So really, the statement is a much more strong one, even though we didn't prove it here. But in principle, if the universe started out just a little bit non-isotropic, things would have gone completely out of hand, and we would not be able to describe it with an FRW model at all. And if it were a little bit inhomogeneous as well. The solution, there are exact solutions of general relativity that we will talk about later in this course, which show that there are highly non-trivial evolutions of space-time. And FRW is not stable at all. Okay, so how come that the universe was so extremely flat, and isotropic and homogeneous at very early times? Now, the assumption of an inflationary period offers an explanation to this. Let's ask, is there a type of epoch in which the universe evolves towards flatness instead of away from flatness, as we just saw? And indeed, that was realized first by Robert Brout, who was a regular visitor here, and he would have gotten a Nobel Prize for the Higgs particle, along with Englert, his collaborator, who did win the Higgs Prize. The two of them, Brout and Englert, also came up with inflation, along with some others, Starobinsky and so on. But Brout and Englert were the first to publish a paper on it in 1979. They pointed to the fact that this formulation of the Friedmann equation also indicates a drive towards flatness, namely when a dot is increasing over time. See, when the expansion of the universe is accelerating, when a double dot is larger than 0, well, then the denominator grows. Therefore, the right-hand side gets smaller, and therefore we get omega gets closer to 1. The energy density was driven towards the critical density, and the universe flattens out. In other words, when we have an inflationary period, when we have a period where a double dot is larger than 0, and we have a period where w, the w parameter, is smaller than -1/3, then the universe will flatten out. You can think of it a little bit like a wrinkly balloon. You blow air into it, and then it flattens out. Actually, this is a picture that is much propagated, but not exactly right. It's not true that the universe behaves like a wrinkly balloon, that when you blow into it, it expands and irons out the wriggles. When you go through tedious, detailed calculations, you find that what happens is that the wrinkles just become larger. They become much larger, and therefore, if you look at a finite size patch on the space-time, that patch becomes flatter and flatter. But overall, it's not that they become ironed out. They're still there, those wrinkles. They're just much, much larger. But we didn't go in. Our math is not capturing that because we made the assumption of homogeneity and isotropy. Anyway. Okay, so this is one of the key reasons why the standard model of cosmology nowadays postulates that the universe started out with an inflationary period of a double dot larger than 0 and W smaller than -1/3. That's also called the inflationary attractor because this is making it stable, right? So whatever the curvature of the universe was beforehand, after an inflationary period, it's pretty much flat. No matter whether it started with a positive or a negative net curvature, spatial curvature, after a sufficiently long inflationary period, you drive it towards flatness. So what are the experimental constraints? Well, the experimental constraints are that the flatness is such that the scale factor during the period of inflation must have changed by about 60 e foldings, by about e to the power 60. Now, the conjecture of an early inflationary period also explains some other conundrums that standard Big Bang cosmology used to have. In particular, at very, very high energies, early on in Planck scale and Guth scale and so on, you would expect that there might be some exotic high mass particles, but we don't see them. And inflation explains that we don't see them because they've been basically diluted away. The universe has expanded by a huge factor during the period of inflation, and that just made them rare. They may be there, but rare. Another conundrum that inflation is addressing is how the universe was filled with matter in the first place. Now, I mentioned that already. The idea was that the inflationary period occurred when a scalar field phi had a large potential. See, remember that the energy density is given by this expression for a scalar field. The pressure is given by that expression. And when the potential is very large of a scalar field, then the ratio between pressure and energy density becomes -1. Otherwise, it can be other things, but when the potential is very large, then it dominates over those kinetic terms, and the pressure is just -1 times the energy density. So during a period of large potential, we have that the W parameter is close to -1. And after the period of inflation ends, after the potential, any system wants to come down from a high value of its potential. After that period ends, the energy that was in that potential went into the production of all sorts of other particles through the usual Feynman graphs. The inflaton particle, viewed as a quantum particle, is a particle that has interaction vertices with other particles. We don't know what they are, no idea, but the assumption is that it has interaction vertices, that it has interaction terms with the particles of the standard model, which means that when its potential drops, its energy will be channeled into other particles. We don't see the inflaton particles because the assumption is that their mass is very high. So we don't see them at the low energies that we now have. They would all have decayed into other regular particles. Okay, so at the end of the inflationary period, we then have what effectively looks like a universe just after a Big Bang. Hot, dense, flat, and full with particles. The conjecture of an early inflationary period also solves the horizon problem, which is the problem that the cosmic microwave background, and in fact the universe itself, looks very much the same in all directions. If you peer a few billion light years in this direction or that direction, you see the same statistics. But what set it up in this way? It turns out that, for example, when you look at the CMB, you're looking at processes that happened many billion years ago, and if what you see there and what you see there happened at different places. And you can ask, well, okay, the temperature of the CMB here is about the same as the temperature of the CMB there, about the same as the temperature of the CMB over there. But what set it to the same temperature, given that the universe, when the CMB was produced, was only like 100,000 years old? Which means that light can only have traveled up to 100,000 light years. But we see the CMB coming from different directions, having been produced at places that at the time that the production of that light took place were much further apart than 100,000 light years. So how can they possibly have been equilibrated? So here we are, we look back at the CMB, and we see one part of the CMB. Here's one part of the CMB there. And then if we go back to a conjectured Big Bang, then you see this event has a past light cone. That CMB photon production event in a different direction also has a past light cone. But since there's only a finite amount of time between the production of the CMB and the Big Bang, those past light cones, and you look at sufficiently different directions in the sky, didn't actually have an overlap. So it's not clear why this physics should be equilibrated with that physics. The period of inflation changes that, because then everything came from one small patch, which, I mean, like all of this physics, even though they're very far apart, if there was a period of exponential expansion before that, then, you know, they can all have the same origin. Well, and then finally, oh my God, we are running out of time here. And I'm already at at slide number 13. Right. How shall we do this?
Triple lecture?
Didn't bring any survival kits today. How shall we do this? There are two things I wanted to tell you about. The details are in here. Well, much of it is text I can scan through quickly. There are two main messages I still want to get across in case some of you want to leave already. I mean, I will just barrel through if you don't mind. But you feel free to leave. What comes now here, the rest of the lecture, is basically a preview of what the content is going to be of my course next term, or what will be part of the course next term. Namely, in the standard model of cosmology today, cosmic inflation, also predicts, on top of the things that we just said, it also explains why the distribution of matter in the universe today is the distribution that we find. And the huge idea that's behind this is that the inhomogeneities in the universe arose from quantum fluctuations. So the picture is this, that inflation was ironing out everything. So we had a period of almost exponential expansion at the in a very early period of the universe, and that made whatever the universe might have been wrinkly before. But because of that period of cosmic inflation, it turned out to be extremely flat with very high accuracy after that. But we see in the universe inhomogeneities. We see that at some place there is a galaxy, and then some other place there isn't, and so on. There's a distribution of matter in the universe. And that distribution of matter has a certain statistics. The theory of cosmic inflation explains that statistics by saying that the original inhomogeneities in the distribution of matter and energy in the universe were due to quantum fluctuations. Now you might think, well, quantum fluctuations, they're so tiny. If you measure them in the lab, you really you need some proper equipment to measure them, quantum fluctuations. And these are quantum fluctuations of the vacuum that are, recruited to explain the inhomogeneities in the universe. And it turns out that quantum fluctuations are normally only large at very small scales. If you look at quantum fluctuations at 10 to the minus 10 meters, yeah, there are plenty. But if you look at quantum fluctuations at a size of a meter, Good luck finding them, right? They're very weak. But during a period of W being smaller minus a third, during a period of accelerated expansion, something happens with the wave equation. Even classically, what happens is that the wave equation freezes. Not the equation, but the solutions freeze. The solutions freeze. A classical wave would stop oscillating. It would stop oscillating. If its wavelength is larger than the horizon created by the acceleration, then that wave's amplitude will be frozen, will no longer oscillate. And the quantum theory of that is very interesting. It means that if you take quantum fluctuations that, as usual, are prevalent only at very small scales, in a universe that's very quickly accelerating, then those quantum fluctuations will stop doing whatever they normally do. They get sort of frozen in as the universe expands underneath them. So you have large quantum fluctuations at small scales, but the universe makes them very large, not in amplitude. They were large in amplitude already at small scales. But no, it makes them very large on large scales. So you can have quantum fluctuations that were of large amplitude, of a wavelength of perhaps 100,000 Planck length, and they will end up being quantum fluctuations at cosmological scales, where they can then serve as the seeds about which the initial distribution of energy condensed. So you could then have, the hydrogen clouds condensing into galaxies, condensing into stars. So quantum fluctuations seeded all structure in the universe. Initially, inflation made a clean slate, and then quantum fluctuations imprinted a particular statistics of quantum fluctuations on that, and those quantum fluctuations then seeded all inhomogeneities in the universe. And that prediction was made in the 80s. In the 80s, they already made the prediction that the statistics of the inhomogeneities in the universe, this is the inhomogeneities in the CMB, the cosmic microwave background, and today, of course, that translates into inhomogeneities in the, or non-trivialities in the distribution of galaxies, that it had this dependence, this is amplitude versus Fourier mode, Fourier number. It's really the spherical harmonics, they are on the sphere, the analog of the Fourier transform. They predicted this kind of curve with a particular echo in here because of resonances in the primordial plasma. And then in the 2000s, evidence was found that this is actually the case. And there were competing theories, but cosmic inflation won out in that competition. And we now think that this is the right theory. So that's one of the things I wanted to mention, and how to calculate quantum fluctuations of fields in an expanding space-time or in the background of a black hole. That will be the subject of the course next term. Maybe just to conclude for today, I mean, I invite you, of course, to read the remaining slides where all of that, what I just said, is explained in some detail. And where I give some introduction to the perturbation theory. So how do you calculate the perturbations around a completely flat universe? But one of the things I wanted to leave you with as well is the possibilities that cosmic inflation offer. See, here is, where is it? Here, the timeline again. We said, how could it possibly have started? What triggered inflation? Now, I'm intrigued by a possibility which is conceptually very nice because you don't really have to make many assumptions here. The idea is that the universe before that had a scalar field. It had this inflaton field governed by the Klein-Gordon equation. And that universe might have been a universe just like ours. It might have had perimeter institutes and dogs and cars and everything. But in particular, it also had this Klein-Gordon field. And that Klein-Gordon field did what quantum fields always do. It fluctuates. And typically, the fluctuations are small and hardly noticeable. But it is possible that the inflaton field fluctuated in a patch a few Planck lengths across, a volume, a few Planck lengths across, maybe 10 Planck lengths across, such that the potential of the inflaton field happened to be close to the Planck energy. A very rare occurrence that you would have almost homogeneous fluctuation that would lift the potential of the inflaton fields to close to the Planck energy for a few Planck lengths across, a patch like that. Extremely rare event, but it could happen at the tip of the nose of a dog. I mean, it could just happen randomly. But you see, if that happens, then you have locally, effectively, a large cosmological constant. And the universe would, at that point, bulge out. It would mushroom out a daughter universe. And for all intents and purposes, that could be our universe. Right? It could be just coming from this tiny fluctuation in the mother universe. I don't know what that would entail, whether it would spread or not. I think it doesn't even have to spread. It could be just, a daughter universe could be just mushrooming out of this mother universe because of a quantum fluctuation. And it would set up exactly that scenario here. You have a universe that might start out with some matter in it, like pieces of the dog, and there might be some curvature as well. But as this local patch of very large potential makes the universe expand by many, many, many orders of magnitude, you have this mushrooming out of a universe which ends up at that point, a little later, being very flat, being very large, and the energy going into the production of all the particles that we see in the universe. So it ends up creating a hot Big Bang scenario after that. Key to this, of course, is that even though it might have started in a tiny patch on the nose of a dog, the thing is that the energy doesn't dilute. The universe expands under that point of this extended potential of the inflaton field, but the energy density doesn't dilute. There's no energy conservation in general relativity, and this is how you can have that dramatic behavior. Of course, this could happen in our universe at any moment too. It's not stable. Our universe, if it has a scalar field with a potential in it, is not stable under this with regard to the production of more universes. Typically, quantum fluctuations would happen and just recollapse, happen and just recollapse. But if it's large enough, the nonlinearity of general relativity kicks in, and it will explode. It will spawn a new universe before the fluctuation can recollapse. So that's an alternative to the Big Bang scenario of just things happening out of nothing suddenly. One moment. This could mean in particular that there's an infinite chain of universes that spawn each other. Yep.
So from what we know from the inflaton, I don't know what parameters are. What's the time scale at which you could expect this to happen? You know, 10 to the something, 10 to the 10.
I don't know. It's a very, very rare thing.
Yeah.
But there is, I should say that it might sound philosophically appealing. I find it appealing, but it also leads to deep conundrums. And the originators of that theory are very much struggling with these things now. Because even though, yes, it's very rare for this to happen, for example, also in our universe, still you have this infinite chain of universes all spawning other universes. And therefore, even the most unlikely things can happen because there's so much space, right? So many universes. There's just so much stage for stuff to happen in. And in particular, if you follow certain lines of reasoning with respect to some measure in the probability space that you may cook up with regards to that, it is possible that, and in fact not only possible but also likely, that in one of those universes, from the matter that's swirling around, matter would organize itself into a brain that dreams all of that. And the thing is, it's not easy to argue that this is less likely than a universe in which people come about through evolution. It's just because it's very difficult to put a measure on the space of all possibilities there. Yeah. And so you run into this. Basically, the entropic principle is big in this. And the entropic principle is an enemy of science. So on one hand, it can be satisfying. On the other hand, we have to be careful that we are still explaining something.
That's also assuming the parent universe is the same laws of physics that we know of in the baby.
Yes, in fact, there are studies that consider the possibility that during such a dramatic event, like the spawning of a daughter universe, some of the parameters of the parent universe might be retuned. Like the fine structure constant might be a little bit different, the mass of the electron might be a little bit different. And so you can have that these universes spawn other universes. You have an evolution of universes. Some of them may be more conducive to life, others less conducive to life, and that's where the entropic principle comes in. We find ourselves in a universe which is conducive to life. But you see, the trouble with this is that we might end up concluding, if we follow that line of reasoning, that we will never explain why the muon is 200 times more heavy than the electron, because it might just be a random tuning that came from one of those spawning of a daughter universe that made life possible. So it could be that the explanation is really an entropic, but it would be much more satisfactory if there was some grand unified theory of the standard model that could explain its structure, rather than being random like the weather. Yes?
Do we know what it would look like if one of these bubbles happened, in the Milky Way or something?
I don't know that. I don't know. I'm not sure anybody knows that. It's a highly nonlinear thing. And I suppose you could imagine, because quantum effects are very important in that, you could imagine that both are possible, that the daughter universe stays connected to the mother universe through some kind of a throat, which might also enlarge, I don't know. It could also be that it becomes disconnected. And if it does become disconnected, think about what that means. It means that you don't have a continuous timeline from the mother universe to the daughter universe. Maybe in our imagination we have that, thinking of soap bubbles. But in practice, the space-time of the daughter universe, if it was completely decoupled from the mother universe, that space-time would have a time variable, or cosmic time if you want, which has nothing to do with the mother universe. The mother universe wouldn't, strictly speaking, wouldn't be earlier than the daughter universe. It wouldn't, right? You would have like bubbles, like soap bubbles going around with no ordering among them. Because remember that those soap bubbles don't have to be embedded in a higher dimensional space at all. Right? If they were, you could still make sense of, yeah, this came from that. But if they're not embedded, they're just separate. but neither earlier nor later. And still there's a causal connection. Yeah, and papers are being written on what observations of current physics in our universe might tell us about the mother universe. What of its properties might have survived through that bottleneck, through that spawning of the daughter universe.
I have a more mundane question. So do we know, based on how flat the universe must have been right at the end of inflation, what the flatness had to have been back at the Planck era?
Yeah, and it's not flat at all.
Okay.
Because if you remember, it goes the other way around. During inflation, the things are driven towards flatness. So the mother universe could have been very wrinkly. Doesn't matter.
Okay. So we know that at the Planck time, the universe was not remarkably flat.
Yeah, inflation doesn't require that. You solve the flatness problem.
Right, it doesn't require it. But so my concern is that it's just shielding what actually was happening before inflation. Maybe it was still remarkably flat. And inflation is just...
Yes, in fact, we would predict that. The theory would predict that. It would predict that the mother universe was itself spawned by a grandmother universe, and therefore went through a period of inflation, was almost flat like our universe.
Right, that's not what I meant, though.
Yeah, but that's what you would expect.
Eternal inflation, whatever.
Yeah.
So we know that at the Planck time, it wasn't very flat.
We don't know
right?
that.
We don't know that. So then we don't know if inflation actually solves a problem.
But remember, independently of whether it was flat or not, after inflation, it's going to look flat.
Right. But if the problem was that the universe started out remarkably flat, now inflation is just saying we don't know anymore whether it started out flat or not.
Well, that's true. It no longer matters. But that's good, because it says that the fine-tuning problem is solved, because we have a mechanism that establishes the fine-tuning. We have an attractor of a differential equation.
No, but if we had...
Okay, but I think we should move that to the post-lecture discussion then, and I close it for today. So Monday for double lecture again.
Yes. So if the universe was still remarkably flat and prior to inflation, why isn't that also a fine-tuning problem?
Well, yes, if you had